Thank you. So this is indeed the title of my talk, which was the same as the title of the course of lectures that I gave in the first week of the school. And it represents work done with Alvaro Mosota, which I've also given here his full name in the Spanish way, Alvaro Mosota Frauca. I give that because of the confusion of the Spanish naming conventions. You may find, oh, hold on a second. What's going on the battery now, I guess. But anyway, if it loses the battery, I'll try to figure out how to plug in the charger. So because of the naming conventions, you may find, if you look up a paper of his, you may find it listed under Frauca rather than under Mosota. And the work is published, posted on the archive here. And as I said, I gave 3 lectures, so this is in a sense an attempt to condense down 6 units of the present lecture into 1 and then add a little bit that I didn't get to in the original lecture, which is obviously impossible. But I will try to add the part that was missing, which was the general derivation or general calculation that shows how, that justifies saying that we have a way of measuring the quantum measure. So let me just read out the abstract and then go on. It summarizes most everything. When utilized appropriately, the path integral offers an alternative to the ordinary quantum formalism of state vectors, alpha joint operators, and external observers. An alternative that seems closer to the underlying reality and more in tune with quantum gravity. The basic dynamical relationships are then expressed not by a propagator, but by the quantum measure, which we'll define. A set function mu, that is a function that takes sets, assigns to every set of histories, which we call E, its generalized measure mu of E. This is, the idea here is that the quantum measure is to quantum mechanics what the Wiener measure is to Brownian motion, for those who are familiar with Brownian motion formalism. Except in special cases, mu of E cannot be interpreted as a probability, even though it's a generalized probability, as it is neither additive nor bounded above by unity. Nor in general can it be interpreted as the expectation value of a projection operator. Nevertheless, I will describe how one can ascertain mu of E, its value, experimentally for any desired event E, any desired set of histories, by means of an arrangement which, in a well-defined sense, acts as a filter that allows to pass those histories which belong to E. So I always start by trying to say a little bit about why I think that I think it's a program of which some of us are involved in trying to replace the usual quantum formalism with one based solely on histories, what I'm calling here histories-based quantum mechanics. So let me just say a little bit about why I think that's a good idea. It has to do with the relation between quantum gravity and quantum foundations. So arguably, quantum gravity needs a histories formulation. That is something which functions as a generalization of the path integral. On the other hand, this is basically because all the observables, if you want to use that word, or the beables, if you like that word better, all the observables or beables of quantum gravity are essentially global in nature. They're never something at a particular moment of time, because that's not even a coordinate invariant notion. The only formulation that really does justice to that is something like a path integral. Conversely, quantum foundations may have, and I think it does have something, so this tells us that quantum gravity has something to offer to quantum foundations. It's telling us that we should really try to do quantum foundations in this histories framework. Conversely, quantum foundations, I think, has something to offer to quantum gravity, because if it can provide us a realistic way of thinking about the quantum world, that's just what we need for quantum cosmology and other extreme regimes where there are no observers and where quantum gravity is important. It also, hopefully, a better understanding of quantum foundations will help us to better understand the concept of relativistic causality, which has a very good chance of being a central notion in quantum gravity. So to make it look like not quixotic, not a crazy idea that we should formulate everything in terms of histories, let me make a claim. I'm not going to prove this, and in fact, it's never probably been completely proved because no one has ever completely, to my knowledge, analyzed the measurement situation, including all the details of the macroscopic instrument and so on. But the claim is that every probability that you've ever computed or anyone has ever computed using the Born rule for ordinary quantum systems can be done from the path integral alone without reference to any of those other things that I talked about, like projection operators, collapse rules, blah, blah, blah. Because all of those things in the end are probabilities of what I'm calling instrument events. So an instrument event, I mean an event that takes place in an instrument. So for example, if the instrument is this idealized pointer, then the pointer moving this way is a particular event. The pointer moving this way is a particular other event. And since the path integral allows us to compute a measure for every event, and since that measure can be interpreted as a probability in the case of instrument events, it gives us the answer directly without going through these other formulas. So that raises the possibility and the question that I put here in the form of a question: can we do quantum mechanics with histories and nothing more? That's what I mean by a histories-based quantum mechanics. What we'll see along the way today, and which in some sense is the goal of the lecture today, we'll see that this question will lead us to a new class of events, and therefore a new, by new I mean one that's not contemplated in the ordinary quantum framework. A new class of events, which I'll call space-time events, or global in time, or distributed in time events, and a new class of measurements, which will reveal the generalized probability or the quantum measure of those new types of events. We'll see a specific example. For those of you who are here in Urbashi's talk, she gave a particular example with two sets of two slits in a diffraction experiment. So everything that I am going to say today will be in the context of a very simple model. I've tried, those of you who may have thought about the path integral or read about it will know that in some settings there's a lot of mathematical complications, even something simple as a non-relativistic particle, because of the continuum of times and technical issues of measures defined over infinite spaces and so on. So here I try to simplify everything as much as possible and bring it as down to earth as possible to a setting where I think one really can do, or I am told by some experts that one really can do experiments, that one can experimentally realize the scheme I'm going to describe. And this setting is what I've called the two-side hopper. Two-side hopper, the name means imagine some system that can only be in one of two places, and in time is also discrete, and at each moment of time it either stays where it is or it hops to the other place. That's the two-side hopper. Here's an optical model for that. It's made, as you can see, of beam splitters here. This thing is a beam splitter, and a photon, let's say, and mirrors. Mirrors are the dark rectangles. And all the photon can do, if we think in terms of its trajectories, it's released here in the zeros beam, the upper beam, which I've labeled 0. It then it encounters the beam splitter, and it either goes through or it bounces off. If it bounces off, it goes in the beam I've labeled 1. If it goes through it, it's transmitted through the beam splitter, it goes in the beam I've labeled 0. And so its whole history is then described by a sequence of zeros and ones, starting with 0, and then either 1 or 0, either 0 or 1, either 1 or 0. So history, here are some examples of histories that the photon could have. It could be just 0, 0, 0, 0, always being essentially reflected at each stage, each beam splitter, or 0, 1, 0, 0, or 0, 0, 1. So history mathematically is just a bit vector, or a sequence of bits. The only thing, so I'll write it when if it's necessary to write it in a general way, I'll label the successive bits by x1, x2, x3. So the general history will be 0 and then either 0, 1, 0, 1, 0, like you see here. So first we want to plug this into a path integral in order to compute the quantum measure, which I'm about to define for you. For those, again, who have worked with path integrals will know that you compute that it deals ultimately with amplitudes, which you compute by accretion. So in other words, the history goes through various stages, various transitions. The particle either bounces off or it doesn't. In each one of those activities, it acquires a certain amplitude. So here it acquires an amplitude for bouncing off this mirror, an amplitude for going through the beam splitter, for example, again, bouncing off the mirror. But the only thing that will be important to us are the relative amplitudes. So I'm going to ignore the amplitudes for bouncing off the mirrors or going from this point A to point B. The only thing that differs from one history to another is this sequence of bits, in other words, whether it was reflected or transmitted at the beam splitter. And so all we need to know is the amplitudes for those two possibilities, and here they are. The amplitude for being transmitted is 1 over, with normalization, is 1 over the square root of 2, and the amplitude for being reflected is I over the square root of 2. So it's a very simple, leaving aside the irrelevant normalization factor, it's just either 1 or I, transmission or reflection at the beam splitter. So the amplitude of each one of these histories will just be a product of 1s and i's with a factor of 2 to some power in the denominator. It'll just be a pure phase, either 1i minus 1, I or minus 1. So this is what I just said. The amplitude is a product of amplitude. The quotes is because I left out the amplitudes to propagate and so on, the ones I mentioned. So the amplitude is given by this product of these I, 1 over the square root of 2, or I over the square root of 2. I'll call the amplitude of that, I'll call the particular history gamma as before. And the amplitude of that history I'll call A of gamma. Now here is the whole definition of the quantum measure condensed into one formula. It tells us that it provides a measure to an event. Now I said in the abstract, it probably went by so quickly you didn't commit it to memory, but what do I mean by an event? An event is nothing but a set of histories. This is the language used in probability theory, and it's arguably the language used in everyday life, too. So when I say that it rained yesterday, which I don't think it did, but that would be an event that didn't happen. But that's a set of histories of the air molecules and water molecules and so on. I say that it was dry yesterday, then that's a different set of histories. So mathematically, an event is a set of histories. And if we want the measure of that event, which classically would have just been its probability, but quantum mechanically is a more complicated object involving squares of amplitude. I think that's familiar to most people. Then here's the formula for it. It's the sum over all histories, pairs of histories, gamma and gamma prime, which belong to the event whose measure we want, with the amplitudes multiplied together, one of gamma prime with a complex conjugate. And if I didn't have this last term, which I'll mention and come back to in a second, I would just be adding up the amplitudes and squaring them, and that's a familiar rule for computing probabilities, transition probabilities from the path integral. However, not all, and the fact that you add and before you square represents interference. However, not all pairs of histories can interfere. So I've introduced this capital theta of gamma and gamma prime, which is 1 when the two histories can interfere, and 0 when they cannot interfere. Now, which ones can interfere? The rule, this is all I should say in the context of the unitary path integral. There are generalizations, such as to open systems, which may or may not affect this. But in the case that we're looking at, which will be a unitary, in fact, I showed it to you, so it's manifestly unitary evolution. In that case, those which interfere are those which share the same final outcome. Those, if we go back to this picture, it's those histories, whatever they may be doing in between, if they emerge in the same beam, then they can interfere. If they emerge in separate beams, they cannot. That's what this capital theta operator is picking up. I'll remind you, I think, that this is familiar to many of you in the form that I referred to just before. When histories interfere, when different ways that an event can happen interfere with each other, the rule is to add the amplitudes first and then square. When they do not interfere, the rule is to square them first and then add. Think, for example, of computing scattering cross-sections. When particles emerge in different momenta, you don't add the amplitudes for the different momenta, you first square. That's a different final outcome for the process. Okay? So maybe I should stop at this point. I don't want too many questions because I won't finish, unlike the school. But if there's anything unclear, yeah. No, it's very definitely not a boundary condition. In this sum, we're going to include all possible outcomes. All possible. This is not a post-selection. In fact, I'm about to say that. It's just telling you which pairs of histories interfere. But both histories that emerge in the upper beam will interfere with each other. They're present in mu of E. And those which emerge in the lower beam are also present and will interfere with each other. But those which emerge in those pairs where one emerges in the upper and one in the lower, they will not interfere. And this theta will be 0. This will be important in the calculation, which I'll add. So that's a good question. In fact, it brings up what I was about to say. So as you can see in what I just described, quantum measure theory, as is the name given to this formalism, this generalization of the path integral, quantum measure theory because it's based on this mu, which we call the quantum measure. By the way, for those who are familiar with it, there's another term called decoherence functional, which is essentially the same thing, but I won't be talking about it. So quantum measure theory is thus defined by a double sum, as we just saw, over paths, which I call the double path. Mathematically, it's a small generalization of the single path integral, which is the one that most people are more familiar with. Some people may actually be familiar with the double path integral in the form of the Schwinger-Keldysh formalism, which is used heavily in thermal field theory. So that may make it look like a more familiar thing to some of you. And the difference is that the double path integral, well, let's look at the single path integral, which is probably more familiar. It computes the transition amplitude, something of the form final state, initial state, something like that. That's also called often the Feynman path integral. The double path integral, or the Schwinger-Keldysh, if you like, path integral, computes instead a generalized probability, instead of a transition amplitude. Since it's a generalized probability, it's the square of amplitudes, and that's why you see two amplitudes here, a double sum over paths. So it's not really a very big generalization, but in a certain sense, it is a big generalization because there's a difference in emphasis. When one works usually with a single path integral, it's always a kind of S matrix inspired idea. You have some initial thing, some final thing. You want to know what's the amplitude of getting from here to there. You don't care what happened in between. You just sum over all of that. Like you don't, depending on your philosophical attitude, you may say nothing happened in between, or I can't say what happened in between because I didn't measure it in between. So the emphasis here is very different. We don't care so much about getting from A to B. What we really do care about is what happened along the way. In fact, one could go further and say, well, look, is there really a final time? I mean, Pace Adrian, maybe there is, maybe there isn't a final time. But even if there is, it's something completely out of our experience, hopefully. We never know when the next nuclear war might start. But anyway, it's probably out of our experience. And so really everything that happens for us happens along the way. And the idea of the quantum measure theory is to shift the emphasis to these events that happen along the way. By focusing on them, we want to free quantum mechanics from all those things that many people here would like to free it from. External agents, wave functions, observable operators, collapse, blah, 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 blah. Just this one mathematical object, the quantum measure. Now to see in which way this quantum measure theory really is more general than ordinary quantum mechanics. I've abbreviated ordinary quantum mechanics by OQM. To see in which way it's more general, it helps to think about the different types of events whose measure one might be interested in. The simplest, so let me list 4 types, 3 of which are amenable to the ordinary quantum formalism, and 1 of which is not. The first one is what I call the singleton event. It's a very trivial, remember, an event is a set of histories. So a singleton event is a history consisting of just, an event consisting of just one history. Very trivial thing. And computing its measure is also very trivial. It's just got a single amplitude. There's no interference because there's no second history to interfere with. You just square the amplitude. And then you could think of that if you wanted in terms of doing separate measurements at each moment of time to see where the particle, the photon was at each stage of that process by which it gets from here to wherever it gets to. So those are singleton events. The second type are instrumental events. I already described those, and I claimed that these are all the events really for which in the textbook formulation of quantum mechanics, those are the only events that one ever looks at, really, and that I claim that the quantum measure gives in that case the probability of that event, in other words, that experimental outcome. A third type that's closely related is what I call here terminal events. These are also closely related to the type that Adrian spoke about. These are events that refer only to what happened at the very end of the process. So in that picture that I showed you, which I won't try to scroll back again, it just all you ask is which beam did the particle finally emerge in? You don't care what it did along the way. Those are terminal events, and they're the kind of ones that the single path integral is normally taken to deal with. Now there's all the rest of the events, which is by far the majority. I mean, almost no events, almost no set of history can be described fit into any of this. A general set of histories describes an event that's distributed in time. It's a space-time event. It's a globally defined event. I'm on the lookout for any better name, so if anyone has a suggestion, please tell me what it could be. As I said, most events are of this last type, and it's these ones that take quantum measure theory beyond ordinary quantum mechanics because it assigns a measure to every event. If you want something more, I won't say more physical, but more to do with the starting motivations, at least my motivations, namely quantum gravity, think of the event that a black hole forms and its horizon has a certain size. It expands to a certain size and then contracts because of the Hawking radiation. That's an event. But can that event be described by what's happening at a moment of time? No, absolutely not, because the very notion of horizon depends on knowing which photons could escape to infinity, which could not, and knowing which could escape to infinity depends on knowing what the gravitational field will be like, not only when the horizon forms, but much later when it's trying to escape. So as I think in Madhavan, I think it was clearly described in Madhavan's talk, how that works. So the black hole formation of a black hole horizon is one of these global events, and if we want quantum gravity to talk about it somehow, then the way to do it, arguably, is through the quantum measure. However, that's all nice, but we don't have the quantum gravity theory and the quantum measure to show you how it works. So we could ask a more modest question. We can say, within the usual framework that people are already familiar and within a regular optics lab that you might find on the RRI campus, for example, I don't think there's one here, but in RRI campus, there's an optics lab. Could you give an experimental content to this quantum measure? This is a question that operationalists like to ask. Many of them will say something like this: well, okay, you define some nice mathematical generalization of classical probability and so on, but can you measure its value? If you can't, to me, it's nothing. I don't give it any meaning. So when someone says that, I'd like to say, no, that's completely wrong. You're unfair. No, that's a very backward kind of positivistic attitude, but I just throw a lot of philosophical swear words at them, and it doesn't necessarily convince them. It would be easier if we could say, well, yes, in fact, yes, I can measure it. And so the rest of this talk is really to say why the answer is yes and how we can measure it. I'm not sort of going over to the operationalist camp, but it's all anything that you can connect to an operation procedure, a laboratory procedure, is obviously, if you can do it, it's very good. So that's what we're going to do. But it turns out, as we are about to, as we will now just see, you can measure the quantum measure without going beyond the narrow confines of the Copenhagen-Luders conception of measurement. That's the name I introduced in the lectures. It just means the usual textbook way you think about measurements in quantum mechanics. For lack of time, we will only treat here the general case. But in my lectures in the school, I did a couple of simpler cases, the singleton events, which I just referred to, and the next simplest thing, which is events consisting of just two histories. And if you have time and are interested and go back and see the lectures, then maybe that'll provide a little extra intuition of what's going on and why we're doing what we're doing. Okay, so so how are we going to measure this? So before I presented to you this two-side Hopper model, this optical model. Now the way we're going to do the measurement is to couple some ancillas to it, and then couple the ancillas to each other into a counter, which is just another ancilla, which is going to read out the final answer as either yes or no. Yes meaning we did find the event E, and no meaning no, we didn't find the event E. So here's the same picture as before, but with the ancillas indicated. For each possible 0 or 1 in the history, there's an ancilla which looks to see whether it really is 0 or 1. So here's this blue circle here and this blue circle here, which is actually pointed to A for ancilla, represent these ancillas. There'd be one coming after each beam splitter. And what it does is it simply copies xj, the location of the photon, to yj, which is its own location. The ancilla could just be some simple thing. The ancilla itself could be some simple thing. Actually, I think we'll have a picture with two output beams and a ready input state, if you like, input beam. And what it does is if the photon were to be in beam 1, the ancilla would make the transition to its beam 1, and if the photon were to be in beam 0, the ancilla would make the transition to its beam 0. Is it clear? So that's a crucial thing. It's essentially equivalent to what people in quantum information call a controlled NOT gate or a CNOT gate. So after all the ancillas are coupled in, the ancillas will be carrying a copy. They'll have extracted information on what the photon did. So let me now show schematically what I just started to say in words, showing the whole setup of how this measurement works. So here on the top in black, thanks to Sumati for this beautiful diagram, on top in black is the original system as it would have been without all the complications, ancilla and so on. And its history labels 0, 1, so on. Now, the first thing that happens is the first ancilla, which I showed just before in blue circle, it couples to the system. That's indicated by this blue rectangle that shows the coupling. And the ancilla, which starts in its ready state, then makes a transition to 0 or to 1 in such a way that it's just what I said, that it copies the location of the photon in the first stage of the process. Then the second stage happens, another beam splitter, then the photon goes either a 0 or 1 beam, and there's a second, oh, this is the first one, here it goes, where is it? Yeah, that's right, this is the second beam splitter, and then there's an ancilla here, which is shown broken, but think of it as one solid blue rectangle that looks only at what the photon did there. It's broken here so that we can see that the first ancilla just carries on its merry way. It remembers what it had found, but it doesn't further interact with the system. And so each new ancilla interacts, carries away a bit of information on what the photon did. And then after the whole process is over for the system, the ancillas are carrying that information. And then they're all coupled together in a certain way that I'll describe, and coupled to the counter in such a way as to give a final outcome for the experiment. Okay, so is the picture relatively clear? So just to recap what I said just before, the measurement takes place in 2 stages. In stage 1, the ancillas copy the system history, and the counter is a complete spectator. It plays no role. And what's important to recognize is that in this stage, it's also independent of what event we're looking for. Everything happens the same. However, in stage 2, where the ancillas interact with each other and with the counter, the event E very much matters. The way we design the couplings of the ancillas to each other and the counter depends on what event E we are looking for. And however, in this stage, the system is a spectator. So the ancillas have extracted their information, and now we process it, but we never interact with the system again. And then stage 3, which is a kind of triviality, but you might want to include it for completeness, is we look to see whether the counter emerged in its upper beam or lower beam, or which I've called clicking in the upper beam. So we listen for the counter to click, and then it's a macroscopically completed. So you put a photon detector or something. What I have to do now to flesh this out is just to describe to you what happens in these 2 stages, stage 1, stage 2. Stage 1 I just described for you. Stage 3 is trivial and we don't have to worry about it, just detecting where the counter, which beam the counter emerged in. The counter looks just like this, except for those who can see it. The counter looks the same. Just to distinguish it from the other ancillas, I gave it a capital R for the ready state instead of a small r. Now, what happens in stage 2, as I said, only one thing happens. The ancillas are coupled all to each other, and each one of them makes a transition to some other state of itself in a way that depends on what the other one, on the coupling. So the whole of stage 2 is just one transition for each ancilla and for the counter. And here are what the transition amplitudes are. Like any path integral, if we want to put this ultimately into a quantum measure expression, we need the amplitudes. And here are the amplitudes for this stage 2. So I'll write the ancilla history. By ancilla history, it just means which beam each ancilla is in. I'll regard it as the momentary configuration. It's not the whole history. It's the configuration before and then after this coupling of the ancillas to each other. And I'll write it as Y1. It's again a bit string because it's just a copy of the history, which is itself a bit string. So to say what happens, I have to say what those transitions among these bit strings, what amplitudes they have. The ready state I just talked about. Now there's sort of 8 different classes of transitions. The only ones that are important for the calculation are these that I'm giving you here. First of all, suppose that the gamma, which is the ancilla's record of what the photon did, suppose that it does not belong to the event E, whose measure we're trying to compute or experimentally observe. If it's not one of the histories of interest, then the ancilla just makes a transition to the down state. It doesn't click. Sorry, the counter makes a transition to the down state. It doesn't click. That's this R going to D. And at the same time, the ancilla doesn't do anything. It just remembers what it had done before. So it makes a trivial transition. The only thing that changes is the counter, which goes over to a negative no answer. And this happens with probability 1. So that's when gamma is not in the event E, then that's the only allowed transition. Now let's take the case where gamma is, what the ancilla has remembered is, the set of ancillas have remembered is that the photon history was one of the ones we're looking for. It's in the event E. And suppose that gamma prime is a second ancilla configuration, which also belongs to the event E. Then we make a transition from gamma R, again, to gamma prime U with amplitude 1 over E. Now, there's two important things to notice here. First of all, since that's what it was looking for, E, it makes a transition to U. The counter will click. And second of all, the ancillas completely mix up their memory. They kind of lose their memory. It's related to what's called the generalization of what's called the quantum eraser, because they make a transition to all other configurations which belong to this event E with an equal amplitude of 1 over E. And that's the most crucial part of all of this. And then the final thing is that if, again, the original ancilla configuration is in the event E, but the final one that you're thinking of it going to is not in the event E, that's forbidden. That happens with amplitude 0 if the counter also clicks. So it's forbidden that the counter clicks and the ancillas go from a configuration in E to a configuration out of E. That's all we need. There's several other cases that you can amuse yourself by working out where either gamma or gamma prime is in E or not in E, and the ancilla is either up or down and so on. They won't play a role, but you can choose them as you please, just subject to overall unitarity, because we want unitarity so we can realize this in a traditional, in a unitary laboratory. That's we don't need to go to a post-quantum laboratory to do this measurement. So now I had a little trouble with latex, so I hope. So the next slide is on the blackboard, and it describes. I introduced a notation for. So we had this little gamma, which represented the history of the system alone. Now we have a more complicated thing. We have a system. We have n ancillas. We have the counter. They're all coupled together in stages in various ways. And so history is a more complicated thing. But for our purposes, all we need to look at is the history of the photon, the final history of the ancillas. We don't have to worry about the final configurations of the ancillas. We don't have to worry about the initial because it just copies gamma. And then what the counter does, you click or non-click. And since we now have two setups to compare, the one with just the system alone and the one with all the auxiliary stuff, we need two different measures. One for what the system would have done without any of that change. That's the measure. So I called it mu naught. Before I called it just mu, but I've called it mu naught, because that's the one which we're trying to really measure. And then we have mu sub e, which is the measure when everything is included. It has an e subscript because remember the way I designed this experiment depended on which event I'm trying to measure. So it's a subscript e. So that's the measure for the system plus the ancillas plus the constant. And in the end, we're just interested in an instrument event or a terminal event, which is the click event, which says that the counter emerged in the upper beam. And what is the, I described it here by this wildcard situation, notation. It's all, remember event is, as always, is a set of histories. This is all the histories where the counter emerges in the upper beam, and it doesn't matter what the ancillas or the photon has done. That's the event we want the measure of in this laboratory setting. And so, now what happens? Yeah. So now we can finish the computation actually just in one slide, well, because I've cheated a little bit, not shown you every detail. If you go back to the first week of lectures, and if you go back to the first week of lectures, then you can see in excruciating detail how these amplitudes are built up stage by stage in the history. So let me just make a claim. It's not, I mean, it's kind of implicit in what we said already. If we trace through how this joint history, ancilla plus system plus counter, the history of that system, how it develops, you see that the only history, and remember that we're interested in only the measure of the click event, so this mu sub e of c, you see that the only histories that contribute have both gamma and lambda, so both this gamma and this lambda, they both belong to the event E. That was the point of the way that I, what does that mean, 5 minutes? Okay. So that was the point of this what's the word for it? Choosing things so certain transition would be forbidden and so on. So you go back and look at that. Stage 2, couplings. What you see is that only those contribute, and their amplitudes are given by the amplitude of this big history with respect to the event E that we're interested in. It's just the amplitude of the system itself, which I've now given a 0 because to distinguish it from the bigger system. So A sub 0 of gamma, the same amplitude, the products of I and 1 over the square root of 2, times 1 over E. E, by the way, did I say, maybe I didn't say, but no one asked me either. This E represents the number of histories in the event E. This is this absolute E, that's the cardinality of E, the number of events in the history. So it's 1 for a singleton event, 2 for an event consisting of 2 histories, and so on. So that 1 over E is what came from this second part of the description of stage 2. Then the calculation just looks like this. We want to I plug it back into the general formula that works for any event. This is the click event. It's the amplitude of every history in that event, gamma and gamma prime and C, complex conjugate, and this theta that governs whether they interfere or not. When I plug in what this A of gamma is, it comes A0 little gamma over E, A0 little gamma prime over E. And now I have to say, what is this theta? What does it mean that the two, when can they interfere? Well, they can interfere if the 2 photon histories emerge in the same beam. That's this theta naught. I've now given it a naught. And they can only interfere when all the ancillas emerge in their final beam. But their final beams, in the same final beams, their final beams are precisely labeled by this lambda. So going back to this picture, you don't get any interference, say, if the first ancilla for gamma was to emerge in the upper beam and the first ancilla for gamma prime were to emerge in the lower beam, there's no interference. So this has to be the same, these two the same, and so on. Counter same too, but we've arranged that by only looking at the U event. So that's what this means. So what I just said in words is just telling us that the contribution of the ancilla to this theta operator, this theta is just a Kronecker delta. You get 1 if the 2 lambda equals lambda prime and 0 otherwise. But notice that lambda and lambda prime don't appear anywhere else. So we just have to do this sum. It's a diagonal matrix, and it has AE entries, number of events. And so you get E. And plugging that back in, we have 2 E's in the denominator, 1 in the numerator. What's left over is precisely recognizably the expression for the measure of mu naught of the system alone with an overall E outside. So this is the result. Within the setup, the measure of the click event is exactly to the measure, the unencumbered measure of the system alone of the same event, corresponding event E, divided by the number of histories in E. Or multiplying both sides by E, we get that the measure that we're trying to measure, mu naught of E, is just the click frequency, because remember, the measure of the click is a terminal event, so its measure is just a probability, experimentally a frequency. So it's the measure of the click frequency times the number of events, number of histories in the event E, and thus we have measured mu naught of E. If you want to, this E is a loss of efficiency, if you like, but because you have to do more measurements, just because you're getting a smaller answer. Anyway, there's not really time to talk about that, so let me just leave you with a question. The other thing which one would like, I think would occur to almost anyone, is, well, you've designed this kind of detector for the event E. Suppose the detector clicks. Does it mean that E really happened, in reality happened? And a lot could be said about that, but not right now. Instead, let me look ahead to what we hope might happen. soon, which is actually building one of these event filters in the real world. And this would represent, if it's done, and there's a good hope that it will be done, it represents a kind of new class of measurements, quantum measurements that one can do, perhaps in a similar sense, but in a very different direction to the way that weak measurements are a new class of measurements that one can do. These new ones, these classes, hopefully, the kind that you really want to think about if your interest is in quantum gravity and relativistic theories. And
Hello. We have time for one quick question, maybe. Okay, if nobody has any questions, then let us thank the speaker again.